Podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to get into the math side of this. So math plus physics equals fun. I bet they didn't know that one.
That's good.
That's a good one. So we want to talk about centripetal force and how it applies to Newton's second law, really.
All right.
And so if we recall Newton's second law, the real meat of the question, of course, was the sum of the forces is equal to mass times acceleration.
All right.
So if we had an object, and I'm thinking of an old test question actually, that had a large right force and a smaller left force, then the net force would be about that.
Correct.
And as a result, there would be some acceleration that way.
All right.
Okay? So the acceleration was positive and right. The mass, of course, is a scalar, and the sum of the forces sometimes is referred to as the net force. And so that's nice for things that are linear. But what if something is changing directions? And if we're really going to start talking about roller coasters, if it's changing directions, say in that loop-the-loop. So when we're inside of the loop, as we talked about in the previous podcast, what's going on mathematically?
All right.
So do you think that Newton's second law is still good enough?
Yes.
Yeah.
Yeah, of course it's going to work.
But the acceleration in this while you're in the loop is not just going to be to the right or to the left.
Correct.
When you're in the loop, what direction is the acceleration?
Toward the center.
Towards the center. So you're saying that we're still good with the sum of the forces part.
Right.
And we're still good with mass times acceleration.
Correct.
But we need to be more specific about the acceleration.
Right.
So
and the acceleration is going to be centripetal acceleration.
Right. So the centripetal acceleration is what we're going to look at. So if you recall from the previous podcast, like when we were at the top, we said, look, the centripetal force had to be equal to the weight plus the normal, because the normal was just perpendicular to the surface.
Correct.
And at the bottom, it was the same story, although one of them could be pointing, or one of them would be pointing in the opposite direction.
Right.
So the net force, and that's just a fancy word for all, would be equal to mv squared over r. And if you really wanted to get into the guts of this thing, then you would have to say, well, at the top, so let's be clear, at the top of the loop, they're going to be pointing in the same direction, so the weight plus the normal force would be equal to this, and you could get into some serious math. If you really wanted to, you could figure out what the scale would read, or the normal force would be, and you have to be careful not to get rid of some things. So there's all sorts of things. You could say, well, how light do you feel? And so you solve for Fn. If we were at the bottom, we would have to have a subtraction sign in there somewhere because they'd be in opposite directions. And we could still ask, well, how heavy do you feel as a result? So it's important to, I guess the point we want to make here is that the second law still works. Okay, but we have to consider the type of acceleration.
When we have these centripetal acceleration, I might be going the same speed inside this loop, but I still have centripetal acceleration.
Yeah, the v value could very, very well be constant the entire time that you're going, but the direction change is going to be critical.
Correct.
So that's just something that we wanted to make everyone aware of, because as you progress through the sample problem on page 431, that's the setup they're going to use to get you going. And as you go through questions 1, 2, 3, 4, and 5, they're assuming that you understand that the sum of the forces is equal to mass times centripetal acceleration.
And it looks like those questions are just asking concepts.
Right.
What happens when you make a smaller loop? What happens when you make a bigger loop?
So let's go ahead and do number 1 for them.
Okay.
I think that's the right thing to do. So go ahead and get us started, if you will, on 1A there.
Okay, 1A, it says, as the mass increases on the right-hand side of the above equation, then the right-hand side of the equation gets larger. What happens to the F net? What happens to the net force?
Okay, so in our experiments, we did rubber stoppers, right?
Right,
And so we had one rubber stopper, and we swung it with some consistent speed. Okay,
at a certain length away from the center.
correct. So R was constant.
Now, as I add mass, what happens?
So we're going to increase M, and the rate with which we were swinging was constant as well.
Correct.
So if M goes up, and I block out that, okay,
Right.
what happens to my number if I increase the mass?
It's got to increase.
So, in other words, the net force would also have to.
Increase.
Okay, so what do we think? Is that a direct relationship, an inverse relationship?
Well, I don't see a square on the mass. I see a square on the velocity. So I would say if the mass doubled, then the force is going to double.
So if we double mass, then
we double the force.
we double the net force. Interesting. All right, that's 1A. What's 1B asking?
1B, it says, if the velocity increases on the right-hand side of the equation, what happens to the net force?
Okay. So you kind of gave it away.
Right.
So in this case, M and R remain constant. And we're looking at the V term.
Right.
And they want to know if it gets bigger.
Correct. What happens to, if the V doubles, what happens to the net force?
So it's V squared.
Right.
So if we double V, then what happens? So what I would do is off to the side, I would say, well, M is the same, and R is the same. But now I have doubled V. And so I put that in a different color there. The squared side, does that apply just to the V term?
Yes.
Does it?
Squared side.
Well, it applies to the V term, but just the V term.
No.
No, I also have to deal
Oh, the
with
2V. I'm
Yeah.
sorry. I thought you meant, does it apply to the mass?
it. So yeah, it doesn't apply to anything with the mass, but I definitely have to square the velocity, but I also have to square
The 2.
the 2. So then
So if I double the velocity, basically I've got 4
square
times.
2V,
Right.
right? So I would have 4V squared, and what happens to my force?
4 times the force.
4 times the net force.
Correct.
And if you really wanted to, you could deal with numbers. If you need to do numbers, I keep telling this to my students, I recommend that you deal with extremes. So, okay, so if you must, use numbers. Okay, then 1 and 2 are your friends.
Right.
Okay, plus, if you want to test the limits, I'm actually, unfortunately, getting into calculus, but this is a very powerful tool that can solve lots of problems. Okay, then 0 and infinity. And don't get scared off by infinity. Just ask yourself, well, what happens if I make this really, really big? So that's on my right side. What would happen to the left side of my equal sign? And so if you must use numbers, 1s and 2s are easy. It's hard to screw those up. And 0 and infinity really are more ideas than they are numbers. And maybe someday you'll get into that in a math class. So go ahead and do 2, 3, 4, and 5. And take a look at the sample problems. So do numbers 2 through 5.
I think those are easy. They're all concepts, really.
Right, and with the hints we just gave you about numbers and manipulation of equations, it shouldn't be too bad. So signing off, this is Mr. White.
And Mr. Sadler.